Okay, now we're going to look in section 2 about intermolecular forces. So we talked about liquids and solids in general. Now we're going to look at the forces that hold liquids and solids together. And the strengths of intermolecular forces of different substances vary over a wide range, but they are generally weaker than ionic or covalent bonds. We're not talking about the bond in a molecule, but the bond between molecules. And the bond between molecules is probably 90% of the time going to be weaker than an ionic or a covalent. There might be a couple that'll be very close to being just as strong, but most of them here are a lot weaker than either an ionic or a covalent holding one particle together. Okay, less energy is needed to break a intermolecular force, okay, than a ionic or a covalent bond. So you're talking about vaporizing something versus breaking that particular bond in a molecule apart. All right, molecules remain intact when a phase change happens. So we're talking about an intermolecular force being broken, we're talking about a phase change happening. So you're still remaining those molecules the same as they were before. And we see an example here in your notes. And a covalent bond is strong, but an intermolecular attraction or intermolecular force is a lot weaker, the one between two of the oppositely charged particles in two different molecules. Okay, the boiling point of a liquid reflects the strength of the intermolecular force. Okay, a liquid boils when the bubbles of its vapor form within a liquid. Okay, molecules of a liquid must overcome their attractive forces to separate and then become a vapor. So your molecules then must kind of split, okay, and separate and form a vapor. But again, it's still the same thing. Okay, the stronger the attractive force, the higher the boiling point. And they love to ask these types of questions on the AP test. Okay, there are 3 types of intermolecular forces that exist between molecules, and we are looking at them. We looked at them last year a little bit. Okay, the first one is a dipole-dipole. Remember, we talk about a dipole, that means something that is polar because it's di, 2. You have 2 poles, 2 ends, a positive end and a negative end. Okay, we're looking at what we call a London dispersion force, or sometimes it's just called the dispersion force. And the third one is hydrogen bonding. And you also have an ion dipole. And ion dipoles are going to be between an ion, like an Na+, and then something that is something that is polar, like water. So there is kind of a 4th type in there, but oftentimes that'll get put into the dipole-dipole group. Okay. All the forces listed above are electrostatic forces, meaning they involve attractions between positive and negative. Okay. Even at their strongest, again, these attractions are much weaker than an ionic bond or a covalent bond. So we look at ion-dipole forces. Okay, and you've got a picture there over to the right. Just like I said, an ion-dipole. That means you're going to need an ion, obviously. Okay, I need something that has like an Na+ or a Cl-, okay, an ion, and a partial charge of a dipole, meaning something that is polar. Okay. What's going to happen here is the positive end of your ion is going to be attracted to the negative end of the dipole. And the same thing on the other side. Then the negative end of your ion is going to be attracted to the positive end of your dipole. If your charge of your ion increases, okay, or your dipole moment increases, meaning the strength of that dipole, a stronger polar, a more positive end and a less negative end, or a more negative end and a less positive end, okay, meaning a difference being more and more polar, okay, then your force increases. And you've got this picture here in your notes, okay, mine's colored, yours isn't, but you see the positive cation in the middle. And then you see the negative ends of the dipoles. So these are the dipoles, or the things that are polar. This is your cation in the middle, okay? And the negative end of one to the positive cation. This is what happens when you dissolve something in water. Water is the polar, and then something like salt, okay? It's going to be my cations, positive and negative, okay? And that's how things dissolve. Look a little closer at a dipole-dipole force, okay? This is where we're going to have 2 polar molecules. because we've got, that's what it says there, dipole, dipole. Two polar. These need to be fairly close to one another, as do all of them. And that is to feel the force between the two of them. Okay? These are weaker than an ion dipole, okay, because it's only a partial charge. We're not talking about a whole positive in a cation or a whole negative in an anion. We're talking about a molecular compound that has a kind of positive end and a kind of negative end. And you see the picture here, okay? I've got these dipoles where we've got a negative end of this one and a positive end of that one. It's going to be attracted to all of the other opposites. So the positive end here and the positive end there and the positive end there. But they're also going to be repelled by like ones. So you're going to have a little bit of both. But the attractions will win out for the ones sticking them together. Okay. In a liquid, polar molecules are free to move with respect to one another. Okay, and like you saw in that picture, sometimes they attract and sometimes they repel, depending on how they are oriented. Okay, the strengths of intermolecular attractions increase with increasing polarity. If you are more polar, then you're getting closer to being like an ion. So I've got a really positive end and a very negative end. Okay, and my boiling points increase as my dipole moment increases because they get stronger. So for dipole moments to operate, the molecules must be, again, close enough to interact. Okay, so dipole, dipoles, weaker than an ion dipole. Okay, now we're going to have the weakest ones here, which are London dispersion forces, and these are between nonpolar atoms, where no dipole-dipole force exists, okay, because nonpolar molecules and atoms do not have a dipole moment. We have no positives and we have no negatives, meaning you've got something like a chlorine-chlorine. These share their electrons equally because they have the same electronegativity. Okay, it's not like I have carbon and chlorine. We're going to have a difference in how each one wants electrons. Nope, you've got the same. So we've got a non-polar. Okay, there is some kind of intermolecular force though. Okay, and we have a guy named Fritz London in 1930 that recognized that the motion of electrons can cause an instantaneous dipole moment, meaning your movement of electrons. Electrons are going to move around, obviously. Okay, and they can actually cause a little bit of a negative end and a little bit of a positive end on a molecule. Okay, if you could freeze the motion of electrons in a helium atom at any given instant, both electrons would be on one side, and at that instant, my nucleus would have an unequal distribution of charge. So at this very second, something happens where the electrons end up both on one side. So that means that end is going to be kind of negative. And the other end then is going to be kind of positive. So if it happens to find an atom, okay, or a molecule that is exactly the opposite when it's next to it, then you're going to have a little bit of an attraction between the two. Okay. Now again, okay, these are very temporary things. Okay, and like it says here, the motion of electrons on one atom will influence a neighboring atom. So a temporary dipole exists. You're not talking about a set one like you have in a carbon-chlorine bond, where the chlorine is always negative and the carbon is always positive. It doesn't work that way. In a chlorine-chlorine or a helium-helium, okay, these are always the same. Okay, they share nicely. The electrons are here sitting in the middle of my bond. Okay, so the only way you get a positive or a negative is if they move. And the strength of your dispersion force depends on how easily the charge can be disoriented. If you can move those electrons really easily, okay, then it's going to be a stronger dipole. And we call this polarizability. Okay, a more polarizable molecule has a larger London dispersion force, and these are the larger molecules. Okay, and meaning radius-wise larger. Okay, molar mass larger. Okay, these are where they have greater numbers of electrons and their electrons are further away. So it's really easy to move an electron, like if this is my nucleus and this electron is way out here. It's really easy to move this around, okay? And that means I can have a positive or a negative end a lot easier than if my electron is in here. Its attraction is a lot higher, okay? And again, your strength of your dispersion force increases with increasing molecular size. Now, it is good to note that dispersion forces operate between all molecules, polar and nonpolar. Okay, polar molecules experience dipole-dipole interactions, but they also experience dispersion. So it's not like you just have one. Okay, everything has a dispersion force. It's just the weaker of everything else, so you don't see it. Okay, let's try a practice problem here, and then we're going to look at hydrogen bonding. Okay, the dipole moments of acetonitrile and methyl iodide are 3.9 and 1.62. And that is just the unit for the dipole. They put a D. Okay, which of these substances has a greater dipole-dipole attraction among its molecules? Well, you can know this a couple of ways. One, by looking at the number. Okay, 3.9. 3.9 is bigger than 1.62. So that means that my CH3CN has the larger dipole moment, has the greater attraction between the two. You can also kind of look at it as to what's more electronegative, okay, versus N or I, and N is way more electronegative than I, but you've also got to be careful when you shove in some different elements in there as well. You want to go kind of on the numbers if they give you numbers. Okay. Letter B, which of these substances has a greater London dispersion attraction? Okay. And here, you got to be careful because London dispersion is based off of size. Okay, so I would need to find the molar mass of both of these two. And when I would find the molar mass of both of these two, you would find out that CH3I is actually a larger molar mass. So CH3I has the larger London dispersion force. And the last question, the boiling points of CH3CN and CH3I are 354.8 Kelvin and 315.6 Kelvin respectively. Which substance has a greater overall attractive force? Now, like I mentioned a minute ago, the higher your boiling point, the stronger your intermolecular force. Okay, so I'm looking at the CH3CN. And the reason, again, that you have a higher boiling point, and meaning a stronger intermolecular force, is because it takes more temperature, more heat, more energy to break those bonds apart, which means they must have been stronger if it takes me more energy to do that. So CH3CN.